All right, so we're going to continue our discussion. Last lecture, once we talked about this high probability, the big OP, small OP thing, we run into some questions. So Gabriel and another student both tell me, okay, this is different from what they are familiar with. So here I'm going to re-explain everything using another way of language. So basically, when we talk about small OP, big OP, the P stands for high probability. And by high probability, we often use this notation 1 minus delta. So here, when delta is very small, then 1 minus delta means high probability. So probability larger than 1 minus delta is called high probability. And how small is called small, right? So often when we say delta is small, we consider something like less than 0.05. And that's considered very, very small probability. So with 1 minus delta, that is greater than 0.95. And that's a very large probability in our statistical sense. And therefore, when we write this, right, we're saying, okay, for any sample size m, for any delta, given those two constants, we can find a neighborhood, very small neighborhood. So this is neighborhood size and it's positive. So we can have the ratio xn over ym less than that neighborhood size. So if we have this relationship, and also, if we have this epsilon and delta goes down to 0 as n goes to infinity, or maybe I should say goes down to 0 as n go to infinity, and we have this epsilon and delta, what? Increases as delta decreases to 0. If we have that, then those two things will be something we can expect. And that's something we usually talk about when we have this high probability convergence. So in other words, you see, the smaller the delta, right, then let me see if I'm right. The smaller the delta, I think I'm making a mistake. The smaller the delta, then we require a larger we will require larger probability lower bound. And in other words, yes, we must allow the neighborhood to be larger. So this event will hold with that high probability. And on the other hand, if we let sample size goes to infinity, then this convergence, this ratio is getting closer and closer to 0. So we can afford the neighborhood size to go down. So these two are the trend we would expect for this relationship to be held. And also, when we talk about high probability, this thing, in statistics, we often think, okay, if this event inside the probability happens with high probability, then we are very confident to say that this event happens. So basically, high probability is kind of like a relaxation of the condition for us to talk about an event. And here we can just say, okay, xn is close to O, small o ym with high probability. So when we say, let me just write this down. So when we say xn is small o ym with high probability, when that happens, it is equivalent to write xn is small opym. That's what we mean. And similarly, if we have xn equals big OYM with high probability, we say xn is big OPYM. So basically, the small o and big O were still carried over from our understanding of constant to constant sequences AN and BN, which we used in last lecture. But once things become random variables, we talk about random variables with high probability. So if that big O, small o relationships still held with high probability, then we change small o to small OP, big O to big OP. That's it. Okay. And now let's come back to the relationships between two fixed sequences. Okay, so still back to this AN and BN. So if you recall, in our last lecture, we talked about these relationships: asymptotic equivalence, same order, and small o and big O, right? We talked about those 4 things. And one more thing we want to talk about today is what we call this. Sometimes in some research papers, you may see a notation like this, okay? It's not greater or equal than, because the equal thing under is become tilde or something like this, asymptotic equivalence. So basically you can see this is something that combines. What does it mean? So it basically combines the greater or equal than, but it's not exactly that. It's kind of like asymptotically greater or equal than. So how do we interpret this? Any idea or any guess from your opinion, given what we have said? Okay, so probably we can think about this. So think about the asymptotic equivalence. How is it different from equal? If we recall our last lecture, when we talk about this asymptotic equivalence, you see, this thing, it doesn't mean equal, right? Because this left-hand side only require us to have the AN over BN to converge to 0. So it's talking about a limit. I'm sorry, to converge to 1. It's only talking about a limit. It's, well, the right-hand side means AN over BN is equal to 1. So 1 is a limit, 1 is exact equal. And that's the same idea over here. So this notation, so in different papers, it may be used to mean different things, but you might consider this to be something that, but you should read the context of the paper. So to me, it can mean one of 2 things. One is that AN is asymptotically larger or equal than BN. So which means that for a small finite n, we may not have AN greater or equal than BN. But as n goes larger and larger, we would have AN greater or equal than BN. That's one way. And the second way is that there exists, I'm going to scroll this up, there exists a constant C positive such that we have AN greater or equal than C times BN for all n. So you see, for the second meaning in statistics, we use this notation, this greater tilde notation for convenience, because when we write this, we can drop this constant and we don't need to care about, sometimes the constant can be very, very complicated, but as long as the constant has nothing to do with n, we can drop it. And we just write AN tilde greater tilde BN. And that means, okay, we can consider BN as an asymptotic lower bound for AN in terms of the order for n. And those constants were just, we just don't care about it. Okay, so this is why some people use those notations just for simplicity. It's an easy way to get rid of those constants that can be quite long to write. So if you pay attention to some of the seminar talks we may have in this quarter, you can see that many speakers, they will only keep the term related to n and probably the feature number, the size, the dimension p in their slides, and other constants were just dropped. Okay, so that's all about the relations. And one more thing, before we talk about our probability background, is the definition of CDF and its inverse, quantile function. So I'm going to spend some time to talk about that today because I think that's very, very important, a very important basic. So I think many of us have learned this, right? The definition of CDF. One of the most important function in probability. So can someone tell me your understanding of what a CDF means? Cumulative distribution function. You can unmute yourself if you want to speak up. Anyone?
It maps elements of the domain of a random variable to the probability that the random variable is sort of on one side of that.
Exactly. Yeah, that's a very good explanation of what the intuition is behind the CDF. So CDF by me is actually measuring a one-sided interval or one-sided domain of the values that a random variable or random vector can take. And then it will give you the probability for that region. Okay, so here we can say that if we have the CD random variable, right, random variable x, and basically the CDF function, we evaluate it at a particular point in the domain of the random variable space. That means this small x is the value that this big X can take. And then this is defined as the probability that the big X is less or equal than the small x. That's it. And in the one-dimensional case, this understanding is very straightforward, right? Less or equal than. How about in the multi-dimensional space? What if this X is d-dimensional? Also the small x. So let me give you this more advanced understanding. So if we have this big X in d-dimensional, right? So we can write this big X out as big X1 to big XD. We write out its d dimensions. Also, we do the same thing for the small x. It's a realization of the big X. Okay? And then, if that's the case, then the fx, when we define it, it is equivalent to the joint probability that big X1 is less or equal than small x1, and big XD is smaller or equal than small xd. In other words, we use the small x to define a region in every dimension. And in every dimension, we have the probability that the big X in that dimension is smaller or equal than the small x in that dimension. And this is a joint probability. So if you think about this d-dimensional Euclidean space, right? This is like, so maybe in the three-dimensional space, or two-dimensional space, it's easier to visualize. So that is, if you consider this is dimension 1, and this is dimension 2. And if our small x is lying right here, right? And then what is that region? The region is actually this. So it's actually this region. And we're trying to calculate the probability of this region. Okay, so that's the CDF. And a very important property about the CDF is its range, okay? So the first important property is that the CDF is between 0 and 1 for all x. That's the range. And it doesn't have to do with the dimension of our random variable. So no matter what dimension this is, the value of the CDF is always a scalar between 0 and 1. And one more thing about this is that we always have an order in terms of the values in the domain and the corresponding CDF. So that is, if we think about it, so we let the lowercase x, we let its every dimension to go to negative infinity. That means for this one, I'm moving it down, I'm moving it left to the negative infinity in both dimensions. And then my CDF will become 0. That's the limit. And if I move both dimensions to positive infinity, my CDF will become 1. So the two limits are 0 and 1. So if we write it out, it's actually we let x go to negative infinity. And when we use this notation, we mean that every dimension of the lower x is going to negative infinity. Then the fx is going to 0. And if we let every dimension of lowercase x go to positive infinity, fx is going to 1. That's the second property. Okay, and a third important property is regarding the left limit and the right limit. Okay, so basically, one thing we have to understand is that there might be some discontinuities. And how do we interpret that? So let's think about one-dimensional case. Okay, so this is d equals 2. And now let's look at d equals 1. So when d equals 1, and let me just draw a graph. So this is my x, and this is my fx. And the values of fx lies between 0 and 1. Okay, and if there is a value x here, such that my fx comes here, but doesn't take the value, and it suddenly jumps to a much higher value here, and then it reaches the value 1, and then stays at 1. Okay, if this is what my CDF looks like, what does it mean? And if I call this value right here x0, so it means that there is a jump. Okay, so that means when my x doesn't reach x0 yet, the fx value is right here. But after it reaches x0 and beyond, the value of fx reaches here. So there's a gap in the middle. And whenever this happens, we say that there is a positive probability mass at this point, x0. So x0 itself carries a non-zero probability. And in other words, it is a discontinuity point of the CDF, right? Because we have a jump here. So that's why, you see, in terms of the calculus and limits, right? We can write this value. We can call it fx0 minus. So what it means is the definition that x is approaching x0 from left-hand side, and the limit of this left approaching. While for this upper point here, I can write it as fx0 positive. So similarly, the fx0 positive is the right limit. So I'm letting x approach x0 from the right-hand side, and then I take the limit. So you see, this is a case where we have fx0 minus doesn't equal to fx0 plus. If x0 is a discontinuity point, Okay, and whenever this happens, we actually can take the difference between the right limit and the left limit, and that is, you see, if I take the difference between these two limits, what do I get? It's actually, if I do this, it's actually the probability mass right at the point x0. So it's the probability that x takes the value x0. All right, so that's it. So by the same induction, we can say that if x0 is a continuous point, its probability mass must be equal to 0 when the right limit equals the left limit. And that's how we define a continuous random variable or continuous distribution, right? So that's something we have learned before. So if you remember that for those common distribution you have learned, like the Poisson distribution or the Gaussian distribution, it's either discrete everywhere or it's continuous everywhere. But for general distribution, it could be a mix, right? We could be continuous here and here, but in the middle, we can have a discontinuity point. And this is that case. Okay, so no matter where there are discontinuity points or not, but these two things, the fx0 minus and fx0 plus exist for every x0. That's the point. And one more thing. So based on our definition, let me show here. Based on our definition of the CDF, we can see that because of this less or equal than sign, we have fx equals fx plus for all x, which means that for any point, no matter whether it's a discontinuity point or not, its right limit is always equal to fx. That's just by our definition. So in this example, you can see that here, we always have this solid point up and this circle down, which means that we let the right limit take the value, but not the left limit. That's just by our definition. If you change the definition of CDF to less than, then the conclusion will change, okay? But this is just our mathematical definition and we stick with that. All right, so that's all I wanna say about the CDF. But I think the good way to really understand it is to think about it in this mix of discontinuity and continuity points. That will make your thoughts much easier, much clearer. Okay, so given the CDF, we can define a quantile function. And I'm going to write it here.
Oh, sorry, quick question.
Yeah.
If the lower limit is the one with circled, what would the interpretation of that be versus the higher one being the solid circle?
And so the interpretation is that so basically you can consider by the name of CDF, the C means cumulative. You can consider this as a cumulative probability. So you add points sequentially to your interval, and then how much is your current cumulative probability. So which this means is that the fx0 minus, it means that you haven't yet add point x0 to your interval. So that's the probability you have. But once you add x0 to your set, then suddenly the probability jumps up. So that's why there is a gap. It's because x0 itself carries a positive probability mass with it. So that left means that x0 is not yet included. Right means x0 is just included. Does it make sense?
Yeah. I was just saying, like, if that bottom one was the solid one and the top was open.
What does that mean?
Yeah.
Okay, if we have the bottom as the solid one, top as the open, it means that whenever we reach this x0, we suddenly include it, and then we go beyond it. So it's just like it's just an arbitrary order of doing things. So right now in the current definition, it means that when we reach x0, we wait and then we add it. But then in the other ways that when we see it, we just immediately add it. But I'm saying that either way would be okay. We just need to be consistent. It's just that the current definition of fx, because it's like the less or equal than. This definition makes it this way. Yeah. Okay.
Clear.
Thanks for the question. Okay, the next important concept is what we call quantile function. And the quantile function, we use the notation F inverse. So then by the definition, you can see it's an inverse of the CDF, right? What we know about CDF is that it maps from a point in our domain X to a value between 0 and 1. Then if we take the inverse, the quantile function will map a value from X and 1, from 0 and 1 to a point in our domain. So that's what it will do. So let me say that here, if we use the mathematical notation, so F inverse is the map. It maps from this interval 0 to 1 to RD. That's our domain for the random variable. And then how does it do? Okay, so whenever F is continuous, it's quite simple. Let's talk about 3 cases. So F is continuous everywhere for all X and strictly increasing. So what does it mean? So when we say this is the case where we're most familiar with, like Gaussian, is this kind of distribution that gave us this CDF. So let me just give you a very simple example. So let's say that 0 is here, 1 is here, and my X takes value in this interval. So it's strictly increasing from 0 to 1. Okay, so then what does it mean here? It means that if I take any interval in my domain, then correspondingly, the probability of the interval, right? So A, B. So as long as I have A less than B, then I have FA less than FB. This is what I mean by strictly increasing. So which means that for any interval with non-overlapping endpoints, the interval itself must have positive probability. Okay, this is equal to the probability A, X lies between A and B is positive. That's what we mean. Okay, and this is the simple case, right? So mathematically, we know this kind of function has a straightforward way to define what is inverse. So here the inverse would just be defined as, I'm using another color pen. So if you want to map, say, what is the inverse of y? So let's say y lies between 0 and 1. So then it means that I just point my y here, right? And I find the corresponding value here. And this would be what I called F inverse y. That's it. So in this case, the quantile is very easy to define. And how can you associate this with the quantile you are familiar with? Let's think about it. If y is 1/2, right? And then we mean, okay, if we choose this point here, then to the left of it has half of the probability, to the right of it has half of the probability. And that's what we call a median. So then the quantile for 1/2 is median. So let me write this down. So if y equals 1/2, then F inverse 1/2 is called the median of a distribution. And if y is 1/4, then we say this is the first quartile. If it's 3/4, then we say it's the third quartile, and so on. So in other words, the quantiles are actually points in our domain, and they are defined based on the CDF value they correspond to. That's the quantile definition. And when the CDF...
I have a quick question.
Yeah.
Is this only true for this specific case in which f is continuous for all x and is strictly increasing, or is this true for all three of the cases?
It's just the case. So we're going to talk about the other two cases soon.
Oh, okay. Thanks.
Yeah, this is just the first case, which is very easy. You have a well-defined inverse of CDF.
Got it.
Okay, thank you. Right, that's it. Okay, yeah, now let's talk about a case which is trickier. What if f has a discontinuity point x0? How do we deal with that? Right? So just as the figure we have already seen, whenever there's a discontinuity point, so let me put it here, x0 and fx. Still, we will use that same drawing, 1, 0, and empty circle, and continue. Okay, whenever this happens, we run into an issue. Because there is a gap in the middle, then a very natural question is, what if my y directly falls into the gap? To help you understand this issue, I can say, maybe before x0, my probability is only 1/3. And after x0, my probability jumps to 1/2. From 1/3 to 1/2. There is a gap in the middle, right? Then what if my y just falls into the middle? And how can we find its inverse? So in this case, mathematically, we don't have a good definition for inverse. But in this case, we can set it. So we can actually arbitrarily define it. So whenever this happens, we would define this f inverse y to be, so I'm writing this sign to mean it's our definition, to be x0. So in other words, for all the y's falling into this segment from the circle to the solid point, we will always define this inverse to be x0. And also, I want to say, we are not reaching the circle. Okay, so just to be sure that, so basically we're going from the circle to the solid line in this whole segment. That is from 1/3 to 1/2 for this whole region of y. Its quantile is the same thing. It is x0. That's our definition. Okay, and now case 3. In case 3, we're going to have this. So f is continuous, but not strictly increasing, which means that we may have a region that flattens like this. So still 0 to 1. So it goes up, and then flattens here, and it goes up. So if I call this A, and I call this B, what this essentially means is that the probability of X in the middle of A and B is equal to 0, which means that adding the points in the interval between A and B would not increase my probability. So whenever this happens, and whenever my y is said to be exactly equal to this value, which point would I pick as the quantile? Again, this is the case where we don't have a mathematical inverse, right? Because all the values between A and B, their CDF values are all equal to y. So it's not a one-to-one map. The CDF here is not a one-to-one map. Then how do we map Y back to a point in domain? Here we need our definition again. And here we define F inverse Y to be A. So we define it to be the lower point in this interval. That's our arbitrary definition. Okay, now we have talked about all three cases. As a recap, for the continuity case, it's very straightforward. Just find the inverse. For the discontinuity point, for all the values within the gap in probability, we define the quantile to be the discontinuity point. And when we have this flattened CDF, we define the quantile to be the lower point of the flattened part. That's all the three cases. So putting them together, we can have a unified definition of the CDF. And I'll put it here. So unifying them all together, the definition of a quantile, my bad, is this. So this is defined as the minimum of all the values in the domain such that the value CDF is greater or equal than Y. That's the definition. And you can see that this definition will actually satisfy all the three cases. For the first case, we can find fx equal to y. And that x, that single value x, will be my quantile. So you see, when I take the minimum, I can zoom down to that single value to make fx equal to y. That's the first case. In the second case, you see, when I have this y in this segment, in the gap, then to be able to make my fx greater or equal than y, I must pick the discontinuity point x0 because the fx0 is this upper point. So it's an upper bound on y, and that satisfies this definition. In the third case, you see, in the third case, for the whole region from A to B, their fx value will be equal to y. So they all satisfy this inequality. And among these x values from A to B, I pick the minimum, and that gave me A. So you see, for all the three cases, I can unify them by this definition of quantile function. And this is very useful if you know this strict definition of quantile function. You can see it will make a lot of sense when you talk about quantile or use quantile in the future. Okay, so that concludes the CDF and quantile part I want to talk about. Do we have any questions? And just as a preview, so here when we talk about quantile, we are talking about the quantile of a distribution. And later, we are going to talk about sample quantile. That means we have a sample from the distribution, let's say n data points from a distribution. And based on those n data points, we can define a sample quantile. But that's not the same quantile as here. There is some equivalence. So for example, if you think about that, your sample defines an empirical distribution, which put a point mass 1 over n at every data point, then the sample quantile is this quantile for that empirical distribution. So there is some equivalence there. But for now, we're just talking about the population version, the distribution, and we haven't touched sample yet. So far, we haven't touched sample yet. So we're just talking about probability. And a key difference between probability and statistics is whether we talk about samples. So that's something we can keep in mind. All right, so
Professor, is there a way to define this for multivariable random variables?
Yeah, definitely. For multivariate variable, all the definitions carry over. It's just that all the less or equal than or greater or equal than will become the greater or equal than or less or equal than in every dimension. That's it. Yeah, just
no,
like
but for the minima, how do you find the minimum like between two vectors if one vector is bigger than the other, or how do you measure it?
So for the no, it's the same thing, right? For the minimum, then the minimum will be taken over every dimension. So basically, you want to find the vectors, lowercase vector x, such that its CDF is greater or equal than a scalar y. The y is still between 0 and 1. And so just like here, right? So just like in our two-dimensional case here, you will find all the x values such that fx is greater or equal than y. And then among these things, right? So among these things, we need to, actually, I think you raised a very good point. So for example, let's say this set becomes a region, and there is points in the region, and every point is, say, two-dimensional. Then when you take the minimum, you have to, I think you have to have something to be addressed there, because it's possible that if you take the minimum of both dimensions, then that point may no longer be in that region. Yeah, I think you raised a very good point. Right, so it's like you take the minimum per dimension, but that point may no longer be a region over here. So I think for the multidimensional case, the quantile, it's actually a little more complicated. You need to modify this part. But if it's a rectangle, so for example, if this thing is a rectangle, then there's no problem. So that the minimum will still be part of the rectangle. Actually, let me step back. Yeah, so let's look at this figure, right? So when we look at this figure, then the definition of the fx is actually, the region is actually defined as a rectangle. It's just half opened. So for this end, it's actually because we define the CDF to be per dimension less or equal than. So we see the boundary is moving this, this, and this. So that's why the shape is always a rectangle. So that's why when you take the minimum in every dimension, then that minimum point is still part of the region. Yeah, so the problem is not there. I don't know if that answers your question, or does it make sense to you?
Yeah, it makes sense.
Okay. Okay, thank you. And let's continue. So that completes our first lecture, the notes. So today we're going to open up a new topic. And I can assure you that this is probably the most challenging part of this whole course. So please bear with it. So after this part, I think the later things will become easier, relatively easier. So this is called the modes of convergence. And to be honest, I think even though many people are my previous students, right? Even though they have learned this before, but it's very, very difficult to forget about it once you don't use it. So then, how can we make this more easy to understand? I've been thinking about this for this teaching, for teaching this time, because we are doing this remote teaching. So communication is not as effective as before. So I think what I want to do is that I will give you some realization of this, of each mode, so that it will make more intuitive sense to you. So let's try to see how this will work. We try to make the abstract concepts to be more concrete. All right, so let's say we'll define 4 modes of convergence, okay? The first one is convergence in law. Or in many contexts, people will write this as convergence in distribution. And I would say this is the most important types of convergence we will use in this class. Okay, what does it mean? So in this class, we write it in xn converges in law to x. So this left-hand side is a sequence of random variables. And the right-hand side is a random variable. It could be a constant, but a constant is a special type of random variable. So we're being general. And in some other books, when people call this convergence in distribution, they may write it as xn converge in D to X. So you will see both, but they mean the same thing. So here, intuitively, what does it mean? It means that as my n increases, the distribution of xn, of each xn, will become more and more alike the distribution of x. So then we are just talking about the distribution. We're not talking about the realizations of xn or x. So let me just give you a very brief idea of what I mean by that. So for example, in this case, right? So if I let my xn to become more and more like a standard normal distributed, and my x is a standard normal distribution random variable, but these two things can still be completely independent. So which means that by independence, I mean that, okay, let's draw a standard normal distribution. And that's a standard normal distribution, the probability density. So by independent, I mean that it could be possible, even though, let's say my xn and x both follow the same standard normal distribution, independent, okay? When that happens, so like after n is greater or equal than 100, I'm just giving you a special case. So whenever this happens, then by my definition, xn converges in law to x for sure. But if we look at their realizations, they could be totally independent. For example, when my xn takes a value here, my x may take a value far away from it. And if I do another draw, then my xn gets here. And maybe my x gets here. So their realizations may be completely independent of each other. So that's why this type of convergence doesn't tell me anything about the distance between two realizations, one each, like the lowercase x and lowercase xn. It doesn't tell me anything about that. It just tells me, okay, the shape of the distribution of x and of xn is similar. So in my case, they are both standard normal. And in statistics, we also have another way to call this. We call this weak convergence. So when you see people talk about weak convergence, it's about convergence in law. And it's weak because there's no tie or no coupling of xn and x. They can be independent, but I just require them to have the same distribution. That's it. In another way to put it is that the convergence in law is about the marginal distribution of xn and x, but it has nothing to do with the joint distribution between xn and x. Okay, so let me put it. So it's only about the marginal distributions of xn and x. And it has nothing to do with the joint distribution xn and x. And to help you understand the marginal distribution and joint distribution, I'm going to draw another graph. Okay, so let me put it here. So this is x, this is xn. So let's still say that they're both normal distributed. So if they are completely independent, I'm drawing the independent case, and each marginal is standard normal. So xn standard normal, x standard normal. So if you think about the two-dimensional density, it will be like a contour. And that contour will be like circle. And we will have dense points in the middle and more sparse points as I go far away from the circle, right? But it will be like a contour like this. If you want to play with it, you can simulate it in R. That can give you some visualization about the two-dimensional Gaussian when the two dimensions are independent. And in another extreme case, I may have my xn equals x, okay? In that case, you see, all my points will lie on this diagonal line. And of course, I have dense points in the middle and getting sparser and sparser as get away from the mean 0. Okay, so I'm going to say this is, to help you understand, this is 0, this is 0, and same here. This is 0, and this is 0. So you see, when they're equal to each other, the points will lie on a straight line. And in these two extreme cases, the joint distributions are very, very different, but the marginal distributions stay the same. So that's why this is an intuitive way to understand that the marginal cannot give you the joint. Even though the marginal stay the same, the joint can be totally different. And when we talk about convergence in distribution, we only talk about marginal. We don't look at joint. So in either case, we can say, okay, xn is converging in log to x, but the joint distribution can be totally different. Okay, that's the first mode we will talk about, the convergence in log. The second mode, another important mode we want to talk about, is the convergence in distribution. Sorry, convergence in probability. We said convergence in distribution already. Convergence in probability. This is another thing that's very, very important for this class. So mathematically, we write xn converge in P to x. So a key difference here is that for the convergence in probability, we do care about the realization of two random variables. So how close is a draw of xn to a draw of x? In other words, the joint distribution matters here. Okay, so the joint distribution of xn and x matters. And how do we deal with this? How do we consider this? Mathematically, the definition is that for any positive epsilon, we have this probability. That is, xn minus x is greater than epsilon. This probability must go down to 0 as n go to infinity. Okay, how do we interpret this? So I think an intuitive way to understand this is to think about realizations. Okay, so here I have a random variable sequence and a random variable. So let's think about their realizations. So here is realization 1. In this first realization, I'm drawing numbers from the sequence and the limit. So let's say that I have x1, 1, x2, 1, 2xn, 1, and so on. And for my limit, I have x1. Realization 2, I have x1, 2, x2, 2, xn, 2, my limit, x2. And I do it for many, many times, okay? I keep on drawing, let's say capital B. x1b, x2b, to xnb, and my limit, xb. So if I draw it for many, many times, What does it mean? It means that, so for a given fixed epsilon, right, I can calculate for how many of the realizations would I have xn greater minus x greater than epsilon. Okay, so for any epsilon greater than 0, let's say fix n. I fix my n, and then I can get the proportion 1 over b of lowercase b from 1 to capital B out of so many realizations. How many cases do I have my xn b minus xb greater than epsilon? So I'm just calculating among all my realizations, the proportion of the case where the nth realization, where the nth number in among all the realizations is greater minus the limit realizations is greater than epsilon. I calculate this proportion. And this is approximately the probability of xn minus x greater than epsilon. So if I let my realization number capital B go to infinity, they will become equal. This is the idea behind Monte Carlo, right? Monte Carlo is that you draw samples from a distribution, and the more you draw, the better you are mimicking that distribution. And here I'm using this to explain the idea behind this. So therefore, convergence in probability is saying that now we are fixing n, right? But as you let n go to infinity, this quantity will go down to 0. That's it. So it's actually out of the many realizations. If you move your n to the right end, then this kind of, I would say violation. By violation, I mean that this number is farther away from the limit than epsilon size. So that violation proportion will become smaller and smaller and finally go down to 0. So think about it. Convergence in probability is that you are having many realizations, and for every realization, you can compute the distance between the nth number and the limit. And that's what we are doing. And then you can evaluate whether their distance is greater than a preset neighborhood size epsilon. Once it's larger than that, you count it as one violation. And you count the proportion of violation, that's this probability. And as your n moves to the right-hand side, the violation probability is getting smaller and smaller and finally to 0. And what that means is that the nth number will getting closer and closer to their corresponding limits. Okay, every realization has an nth number and a limit. So we care about them both. So that's why you see, we need the realizations to be coupled, right? So each nth number must be close to its own limit. So this can happen. If we don't have coupling, it doesn't happen. So that's why the convergence in probability is really about the joint distribution of xn and x. And it's not just about the marginal distribution of the two. Because if you think about the previous independent case, right? If this number, the nth number, and this limit, they are independent, then even though they follow the same distribution, their numbers could be totally unrelated. So there's no guarantee that the violation would be small. Violation proportion would be small. Does it make sense? So I think this is the key part of the convergence in probability. And I think the abstract part can be better understood by considering those realizations. Okay, so any questions or anything that is not very clear?
I'm just curious, like what's the mathematical definition for the convergence symbol?
Sorry, I think you were cut off. Though I didn't hear the last word.
Like, what's the mathematical definition for convergence in law?
Oh, yeah, that's something I didn't talk about yet. Good point. Yeah, I just directly jumped into convergence and probability. Yeah, let's roll back. Mathematical definition of convergence in law is that we have the CDF. Let me use a different color for contrast. So the definition for mathematical definition for convergence in law is that we have the CDF of xn at a value x converges to CDF of x, the limit, at the same value x for all x continuous of fx. So what I mean is that we require there's point-wise convergence. So for any value in the domain, okay, as long as the limit CDF is continuous at that value, at that point, we require the CDF function as n goes to infinity for every xn, the CDF function at that value is convergent to the CDF function of the limit at that value. That's it. So the convergence in law is defined as the convergence of CDF functions. So for every random variable in the sequence here, it has its own CDF, right? So we have a sequence of CDFs and we have a CDF of limit. So we are evaluating all the functions, right? You see CDF of x1, x2, x3 to xn, and so on. And here the CDF of x, we evaluate all the CDF functions at a point x. As long as the point x is a continuity point of the limit CDF, we require that these values at x must converge to this value at x. That's the requirement. And so you can think about this you can think about this as the convergence for all x. Okay, that's easier. But then we need to make some exceptions for discontinuity point. We don't care about that. So that's why later people make this more general definition to just restrict this requirement or definition to continuity point of the limiting CDF. And that's why you see by this definition, the example I'm giving here satisfy it. Because after n reaches 100, all the CDF functions of xn is the CDF of standard normal. And that's the same CDF of the limit. So the CDF functions are exactly equal, then this condition holds for sure. And in the textbook or in the notes, there is an example for you to understand the case where we have a discontinuity point, but that doesn't matter. But I'm not going to talk about that here. I can leave that for your reading. I'm just going to give you the intuition here. And one last thing I want to say about this, why this is so important. Because later when we learn the central limit theorem, it's actually about convergence in law. Okay, central limit theorem, put it here. So you see, what do we mean by central limit theorem? It's essentially that when we have many IID sample data points, right? We have IID draws from a distribution. No matter what that distribution is, the average of my NIID draws will become more and more like normally distributed. And that normal distribution is the limit. And that's central limit theorem. So, and that's a very important application of the convergence in law. Okay, and also talk about the convergence and probability. Something we have learned in undergrad, the law of large numbers, that's an application here. So we're still about the NIID draws, and we take their average. So convergence and probability is saying that as our n goes to infinity, we have many, up to infinity number of data points. their average will become more and more concentrated on the population mean. And so in that case, when we have large numbers, this limit is a constant, the mean, and this is the sample average. So we have every sample, we have the sample average as a sequence, random variable sequence, because every sample size will give me one average, right? So the sample size defines a sequence, but the limit is a constant. So you see, those two things can simultaneously exist. Convergence in probability to a constant and convergence in distribution to a Gaussian random variable. We'll see that later. Okay, so that's convergence in probability and convergence distribution. So these two things are the most important things to keep in mind for this class, and we will use most of them. We'll use the most in our later applications. Okay, so next is about the third convergence mode. And in this book, it's called the Ferguson book, the large sample theory book. So this is called the convergence in the Rth mean. And how do we define it? So here we have given an R positive. So the definition is the expectation of the absolute difference, xn minus x, the limit raised to the power R, is convergent to 0 as n goes to infinity. Okay, so you see in this definition, we still need that coupling or the joint realization. So basically, you see, I'm still thinking about my realization, right? If you think about it, then I can say that what I have is, so let's say fix and n. If you recall the last page I just wrote, so here, I'm going to realize this expectation using my B, capital B realizations. And this is approximately 1 over B, summation lowercase b from 1 to capital B, and my realization xnb minus xb raised to the power R. Okay, you see, given my realizations, this is approximately the expectation I'm interested in, right? Expectation is actually the average of my realizations. If my capital B goes to infinity, they are equal. And this convergence in Rth mean is saying that as I let my n go to infinity, this thing will go down to 0. That's it. So you see the key difference here is that I'm calculating the average of the Rth powered absolute difference. I'm not just calculating the violation rate. You see, in the high probability, or sorry, in the convergence in probability case, I'm putting it back here. You see, I'm talking about this violation rate right here. And that's the proportion of realizations where the nth value is outside of the absolute neighborhood of the limit. That's what I'm doing here. But here, I'm just directly calculating the difference, raise it to the power R, and average it. So you see, it's two ways of evaluating the distance between the nth value and the limit. That's the only difference. But still, we're looking at the joint realizations, right? They are realized at the same time, and I have to do the coupling. So therefore, you see, this is still about the joint distribution of xn and x. It's not about margin only. And why do we care about this? In statistics, I think many of you might have heard of the mean squared error, right? Especially if you have taken the 201B I taught before. I think that's something we talk about a lot. And if you think about the mean squared error, it's actually R equals 2, right? So R equals 2. Then this result is related to what we call the mean squared error, or short as MSE. So that's why we care about this, right? Because we want our estimator. So if you think about our xn as our estimator of sample size n, and if we think about our x as our parameter of interest, then clearly when we talk about MSE, right? Then MSE is just this expectation of xn minus xn squared. And we want this to go down to 0. We want this to go down to 0 as sample size go to infinity. That's why the convergence in the Rth mean matters in statistics. Okay. Before we conclude today, I will introduce the last mode, but the most difficult one to understand before we finish. This is called convergence almost surely. Almost surely. And often you will see people write this as A dot S dot, convergence AS. And this is the most important thing, actually, I would say, if you take a measure theory class or analysis class, this is very important. But in statistics, it's not used so often. So that's why we put it in the last. Still, I think it's very good to know about it because this is the strongest convergence of all, if you think about it. And what does it actually refer to? So still, think about this realization. So what it actually requires is this. I'm going to write down the definition, okay? So it's written as xn converge as to x, okay? And when we write this, what we're actually implying is that the probability that the limit of xn is x. This event happens with probability 1. So that's why this also called as with probability 1. Sometimes you will see people writing this way. When they write with probability 1, they mean almost surely. And then what does it mean? It means this. If we still think about our realization, it means that my xn1, the first realization, will converge to the limit of my first realization. And second realization, the sequence converges to the limit too. So does the capital B realization. So in other words, in every realization, I require the sequence to converge to the limit. So that happens within every realization. It's not across the realization in some way. It's just like if we have, okay, I can write it this way, still using my realization way. So if I'm checking this, I'm using an indicator function to check. Does my sequence in this realization converge to its limit? I'm calculating this proportion. And again, this is approximately equal to the probability that the limit, there's a limit here. Sorry, I forgot to put here. My bad, there's no n here. Yeah, this is right. So this is approximate this one. And as my capital B goes to infinity, they're equal. So this is for all my sequences. And so what this says is that this thing should have probability 1. So that means this thing happens almost surely. Yeah, that's where the almost surely comes in. So among all the realizations, I can almost surely say that they all converge to their respective limits. That's it. So that's why you can see why it's so strong. It's not, unlike the convergence in probability, it's not just about whether the nth element is in the neighborhood of the limit. Unlike the convergence in arithmetic, it's not just about the distance between the nth element and limit. It's actually about whether each sequence does converge to a limit. So we'll stop here for today. And next time we'll try to give you some more concrete examples to let you see why we can have convergence in probability, but not convergence almost surely, why we can have convergence in the arithmetic, but not convergence almost surely. So those are some very interesting counterexamples we want to see. But still, I think for today, maybe we are not going to give you a homework today, but I think the main homework you can do yourself is to really try to understand the 4 modes of convergence, and especially the first 2 modes. If you cannot understand the last one, the most abstract one, I put it here, I think that's something you can leave out for now, but please make sure that you understand the difference between convergence in distribution and convergence in probability, because we will use those 2 most often in this class. Okay, thank you very much, and I'll stop sharing and stop recording, and we will see you on Thursday. Okay, so, and for those of you who have enrolled in the seminar class, we will start at 11. So see you then, bye.
Thank you, bye-bye.
Thank you.